Okay, so now let's go ahead, right, to look at density matrix again. This is from the last lecture, right? Basically, we try to make it very clear what is pure state and what is mixed state. The most important thing is that sometimes we get confused. We thought that pure state means the basis state 0 and 1, but not necessarily, right? Because the so-called basis state, just because we call it basis state just because we decided to use those two vectors as the basis. Any vector can be used as the basis, right? So anyway, pure state, even a superposition is a pure state because it's a well-defined state for a well-defined vector for a state, right? And when we measure it, like in this example, we just follow what we have learned. The probability of getting 0 and 1 are respectively 1 over 4 and 3 over 4, which are just the square of the magnitude of the coefficient. Right? That's the first thing. And then we talk about the mixed states, right? Mixed states is that we again acknowledge that in principle, every state is a pure state. It can be a very big state, right? But because we do not know the incomplete information, so we describe it as a mixed state. For example, with 100 electrons, we may have 25% 0 and 75% 1. When you try to measure it, you still get the same probability distribution, but this one actually have a lot of different states, but we just don't know which one is which. If we know, we actually can make the whole system a pure state also. But now we just treat individual electron as it is, and each of them has a pure state, but we look at it as a mixed state because we don't have the complete information. And finally, sometimes even it is a very simple system like one electron, but if it is entangled to the environment, then we also treat it as a mixed state because we don't know anything about the environment. Or in other words, you have a big system which has a pure state. When you try to describe the individual system, then you can treat it as a mixed state. Okay? For example, if you try to measure the electron, the probability of getting 0 and 1 again is 1 over 4 and 3 over 4. So this you can think more, but any questions? Now if no, then we move forward. Then we try to define something called density matrix. This is very useful for us to discuss the mixed state because we do not have the complete information, but we can construct the density matrix. But of course, it can be used for pure states also because pure state is also a special case of the mixed state. But basically, we say that, okay, now you have a mixed state because you don't have the complete information. And we say maybe there are k different pure states. Like here, I have two different pure states, right? One is 0, one is 1, right? And here I might have k pure states. Thank you. So it might go from psi 0 all the way to psi k minus 1. And each of them has the probability of, or proportion of P1, Pi, right? The way we construct the density matrix of this system is to sum over the outer product of each state and weighted by their probability or their proportion. Right? It looks very complicated, but we already tried one time with the pure state. Again, in a pure state, how many pure states do we have? 1, right? For one pure state, we have 1 pure state, of course. So this pure state, let's say it is 1 over square root 4, 0 plus square root 3 over 4, 1, right? This is given. So what is probability to find this state in this mixture? In this whole, this is a pure state. What is the probability of finding this mixture? 1, right? Because I said it's pure state, you just said 1, right? So we follow the equation carefully. So when you do this type of math, it is very confusing because we are not used to work on linear algebra, right, in EE most of the time. Actually, signal processing, etc., you have a lot of this. But let's say we are not very familiar. You just be very careful to follow the definition. Don't make mistakes. So it says sum over all the pure states. Yeah, k is 1, so I only need sum for I equal to 0, right? And then I plug in P0, size 0, outer product 0, size 0, right? So P0 is 1 because all of them are 1, and then outer product of this state. Again, when you do outer product, you have a cat, you have a bra. So I plug in, and you need to be very careful in doing this multiplication, but these are just elementary multiplication that you learn in elementary school, just distribution rule. But you be very careful following the order. You cannot swap them easily. Then you will get this. And then I tell you, when you see something like this in the computational basis, 0, 0 means the 0th row, 0th column. So you are going to put 1/4 to here. This is 0th row, first column. You put it here, right? So you repeat this, you will get the density matrix. So I won't repeat here, but remember this. Now, today we will look at the mixed state example and try to practice from there. But I want to remind you that whenever you don't know the matrix, just follow the rule. When you have bra, you have a cat, just put a vector column. You have a bra, put a row vector, and then just do the multiplication, right? Row times column, first row times first column. Sometimes I call it 0, so please follow me, right? Sorry, I keep changing. 0th row, 0th column. Then this will give me the first element, right? 0th row, 0th column. 0th row, first column. 0th row, first column. It gives me this one, right? That's how you fill up this matrix. Just follow the rule. So let's take a look at the example. It's just a continuation, should be simple. Now, like given, now I tell you that I have a mixture. We have, let's say, 25%, right, which is 0.25 of them are 0, right? And then the second population is 75%, 0.75, which is psi 1, they are 1, right? So what is the density matrix for this system? Well, just follow the rule. All of you will be able to do it if you do it carefully, right? So I write down the equation, summation I equals to 0 all the way to k minus 1 pi psi I, outer product of psi I. Then we do it term by term. Start with I equal to 0. What is that? P0, psi 0, outer product psi 0. Is this okay, the first term?
Yeah.
Just a mechanical substitution, right? Then I go to the second term. What is the second term? Of course, you need to recognize that k equals to what in this system? How many population do we have? How many different pure state do we have? 2, right? I know it's very simple, so I wrote already. K equal to 2, right? So my maximum is going to be only P1, psi 1, outer product psi 1, right? So with this, then I know I can substitute what I have. P0 is 0.25, and then this is outer product of 0, 0, because I already say that size 0 is 0, just a name, right? I already defined this size 0 equal to 0. And then plus 0.75, 1, outer product 1. Let me make sure I'm recording. Okay. Is this okay? Yeah? Then this is easy. I'm done. Actually, I'm done. But how do I write it in matrix form? Again, 0, 0 means the 0th row, 0th column, right? So this is 0.25. And 1, 1 means 0.75. How about others? This just means what? If I don't have the term, it just means plus 0 times 0, 1. Plus 0 times 1, 0. Right? So here I put 0. Okay? And that's the density matrix of this system. Very simple. Looks like very simple. Indeed, it is very simple. Yeah. Okay, so here I go back to here. I'm trying to say that I have a mixture that I might have 25 electrons that I know that they're pointing at zero state, 75 at one state. That's what I mean by population, right? But then you don't really need to talk about population. After all, is that the information I know is about this system, 25% of them are 0, 75% are 1. Yeah, good question. Yeah. So that's it, right? It looks very easy, right? And indeed it is easy when you are doing the basis state. Okay, so now you know how to compute the density matrix. You are not familiar, but you just keep practicing. That will be okay, right? It should not be difficult. Then let's look at the property of density matrix. Whenever we claim something is a density matrix. First of all, if I have a system that I have n pure states. Is that why? This is wrong. I'm sorry, I said the wrong thing. I have an n-dimensional system. Okay, I have an n-dimensional system. Then the matrix is n by n, right? For example, here is two-dimensional, 2 by 2, right? In order to describe this system, I only need n square complex number, of course. No. N square real numbers, right? Because that is just the, actually it can be complex, sorry, n square complex number. So you need 2n, right? This is the complex number. It can be complex, right? So I forgot, and then how do I come up with complex? Because you are doing this outer product, right? And this outer product, you can have I, right? You can have complex number. So eventually you can have complex number as the coefficient that goes into the matrix. That's how I recognize it. So you need n squared complex number, which actually save a lot because you can have trillions of possible pure state, and that actually need a lot of number to represent. So using this density matrix, you use smaller numbers of number to represent the pure state. Okay, for pure states, if just for one pure state, then it's different. You actually need to have more number, but you get rid of the phase. That's the first thing about this n by n matrix. So you kind of condense it, right? All the density matrix are something called semi-positive definite. So what is the meaning of semi-positive definite? It's just a property of the matrix. And it means all eigenvalues of rho are larger or equal to 0. That's it. Okay, the eigenvalues of rho are larger or equal to 0. So we are talking about matrix. So this is like number. For number, you're talking the number are positive or larger than 0, right? But we're talking about matrix. When you say it's semi-positive definite, then the eigenvalues are larger or equal to 0. Or equivalently, this is like to say for any vector, right? You give me any vector. The expectation on this vector will be larger or equal to 0, right? So we talk about expectation value of operator, right? But operator is just a matrix. So rho is also a matrix. So you sandwich this with this vector. You give me any vector. You do this operation. You find that this is larger or equal to 0. Okay, this is another thing. Finally, it's also equivalent to that the rho there exists a matrix A such that rho equals to A dagger A. It means that you can decompose row into this product, right? You can always find a matrix, so the row becomes A dagger A. You are not going to use this formula. Sometimes we may use this in this class, but this one will be useful in other more advanced treatment, right? So this will be something that you can pay attention to. But this just to give you the definition of what is the positive semi-definite. Now, but this is just saying that a density matrix is PSD. Also, a density matrix is Hermitian. Row dagger equal to row. And this is not difficult to understand, right? In some hand-waving sense. If you look at the density matrix, it basically is diagonal. Let's say in this special mixed case, it's related to the probability, right? It's related to the probability. So these is eigenvalues. So these eigenvalues must be positive, right? Because we're talking about density, right? So that's why it's Hermitian. Of course, this is not a proof, but you can correlate a little bit like this. So it's Hermitian. Another is that the Ch6 is 1. The sum of the diagonal element is 1. Again, this is not difficult to understand because if we're talking about this, for this example, talking about the probability of getting sum of different pure states, of course, you need to sum it up to be 1, right? Just a way to memorize, but it's not a proof. You can prove it, right? And then finally, what is a density matrix? It is a matrix that it is PSD and also the diagonal, the trace is 1. You don't need to memorize this, but whenever, just like when people ask you what's a Hermitian matrix, the first thing you think about is H dagger equal to H. You also think about that the eigenvalue is real. When asked you what is unitary matrix, you know that U times U dagger equal to I. And you also know that each column are orthogonal to each other, or it preserves the inner product of the transformation of any vector after transformation, right? You might forget how to prove it, but this is something you know right away, right? And similarly, when people talk about density matrix, there are so many things. The first thing you think about may be, okay, it must have Hermitian because it has real eigenvalue, because related to probability. Or the trace is 1. And then it's PSD. Maybe you forgot what is PSD, fine. But as this, okay, it is PSD, trace equal to 1. Right? So familiar with this. Just like when you talk about identity matrix, you know immediately is 1, 1. Right? You don't need to like check the test book or Google. Right? So please have this sense. Okay? So let's look at the trace of the density matrix a little bit more just to prove, right? So this is also easy. For example, we just say that the trace of any density matrix is what? 1. Right? So let's look at the, what is this slide? Slide 7. We have the pure state, right? So the trace of the density matrix equals to the trace of, you forgot I copy here, 1 over 4, square root 3 over 4, square root 3 over 4, 3 over 4, and the trace is 1 over 4 plus 3 over 4, right? Which equals to 1. That just proves what we said. Okay, we did not really prove the derivation, but and then another, let's see if it's really true. Slide 8. I think it's slide 8, right? 7, 8, yeah. It's a mixed state, right? Even it's a mixed state. What is the trace of the density? It is equal to the trace of 1 over 4, 0, 0, 3 over 4. Again, the trace is 1 over 4 plus 3 over 4, which is equal to 1. So in the future, if you come up with a density matrix with the trace not equal to 1, you know you have done something wrong. Okay, then you can double check. Okay, any questions? Okay, if no, then how do I know whether it's a pure state or mixed state if you give me the density matrix? They all have the trace equal to 1. So there's another way to check it is that, or this is not checking, but this is just the theory, right? You can prove it. We don't prove here. The trace of the square of the density matrix equal to 1 if it is a pure state. Is less than 1 if it is a mixed state. Okay, just take it as granted, or you can go to prove it. It's not difficult to prove for some of them. So let's just look at an example so we get very used to matrix multiplication and products, right? So let's look at the pure state. We use the same example, right? We say rho equals to 1 over 4 square root 3 over 4. No, 4 should be at the only square root 3 over 4 square root 3 over 4 3 over 4, right? So the first thing I need to do is to calculate rho square. Okay, it's troublesome, but let's do it. Treat this as a tutorial class. And you need to be very familiar with this. Square root 3 over 4, 3 over 4, 1 over 4, square root 3 over 4, square root 3 over 4, 3 over 4. What is the first element? Top left. How do you find it? Can you give me the answer? Anyone? What was that? 7 is, can you tell me how to calculate? 1 over 4 times 1, let me write down, 1 over 4 times 1 over 4 plus square root 3 over 4 times square root 3 over 4, right? Am I right? Okay, that's the first diagonal element, right? How about this one? I don't care. I don't want to calculate because the question did not ask me to find the matrix. You only want to find the trace, right? So this is something you can save the time, right? Then how about the lower right? What is that? It should be, can someone tell me? Square root 3 over 4 times square root 3 over 4, and then? Plus 3/4. Thank you. Yeah, so really you need to be very careful in matrix multiplication, right? This row times this row, this column give you this. This row times this column, it's just like inner product. Remember, actually what you're doing is just the inner product. Row times column, bra times cat. Actually, that's what you're doing. Then you get this, right? So this one give me what? 4 over 16, right? With something that I did not calculate. And then this is 3 plus 9, 12 over 16. Correct? Yes. So that what is the trace of rho square? 4. Oh, yes, correct. So here I have a typo, should be 16, not 14. 16, right? Equal to 16 divided by 16 equal 1, right? So that is correct, right? It check. We just check whether this is correct, right? Very often, just for your own knowledge, you just take some numerical example, then you can check whether the equation is correct or wrong. And that saves you time. Okay, then let's try the mixed state. Now the mixed state is rho equals to 1 over 4, 0, 0, 3 over 4, yes. Right. So this is easy. What is rho square? 1 over 4, 0, 0, 3 over 4, 1 over 4, 0, 0, 3 over 4, right? If it is diagonal, it is very easy. You just multiply the diagonal elements, right? So this is equal to what? 1 over 16? 9 over 16. Very good. Any question regarding this? Now, of course, you can again do the inner product, treat the row column inner product with, row vector inner product with column vector to get this one. Row, right? Bra times cat, bra times cat, bra times cat to get the 4 elements, right? So this one gives us the trace of rho square equals to 1 over 16 plus 9 over 16 equals to 10 over 16. Yeah, 5 over 8, which is less than 1. Again, this is correct, right? Just to practice. I know it's boring for some of you, but is there any questions? Good. So we are very familiar with density matrix now. Rho, the trace of rho is 1. Trace of rho square is 1 if it's pure state. It is less than 1 if it is a mixed state. Done. Very simple. So now let's look at the expectation value. This one I mentioned before, right? If it was not clear, please just take it for granted. We did not prove it. If you have an operator, you want to know, actually we prove it. In the measurement, you do some measurement, you can get different value. And the value you get are the eigenvalue of M. Remember? Right? Like the sigma z, you can get either half, or let's just call sigma z, you can get either 1 or negative 1. Right? So this time I get 1, next time I get negative 1. So depends on the state. I may have more 1 than negative 1 or more negative 1 than more 1. I add them together, do the FH, then I get the so-called expectation value, right? Basically, this is the so-called mean, right? The mean value I will get. Just like gambling, right? You have different possible outcome. And then what is the FH value you will get? Okay, so how do you find it? If I know the state is called V, then it is just this sandwich, right? You apply M to the cat, and then inner product with the bra. This gives you the expectation value. Okay, so no matter what, whether you know how to prove it or not, doesn't matter. You need to memorize this. This is the expectation value of an operator in the state V. Is this statement clear? Then why do I want to do this, right? This is easy, right? I'm talking about pure state. For example, what is let's do one exercise, right? The expectation value of sigma z in state 0, right? This is just some numerical example to help us to agree that this is the correct result. So what is sigma z again? Do you remember? Sigma z in matrix form, what is that? 1, 0, 0, negative 1, right? What is its eigenvalue? What are its eigenvalues? Plus 1 minus 1 is because this is diagonal. We already said that. Sometimes I confuse with E225, so I believe I said that. If the matrix is in the diagonal form, then every element along the diagonal are their eigenvalues. Did I say that before? I don't know, but this is prerequisite. So anyway, so agree with me, right? So anyway, I think I said that, yeah. Then here we say lambda 1 equal to 1, lambda 2 equal to negative 1, right? So what is the measurement for what is the eigenvalue for 0? I mean, for 0 state, what will be the measurement outcome? Is it 1 or negative 1? It's 1, right? So if you keep measuring it, because I give you 0, right? 0 state, right? You can keep measuring it. You only get 1. So what is the FH value in your experimental measurement? 1, because every time I get 1, right? So let's see if that is correct. Now I use this equation to find the expectation value. What is V now? What is the vector now? The state is 0. Yeah, 1, 0. But I put in bracket, so it is 0. And what is M? Of course, it's sigma z, right? That is what I'm measuring, right? The operator corresponds to the observable of my measurement. And then yes, like what you said, now I need to use the matrix form. You can use many different forms, but I use matrix. This is 1, 0 row, right? 1, 0, 0, negative 1. And then multiply column, 1, 0. And you go through the math. Let me go through the math. 1, 0. This is just 1. And then 0, which gives me 1. This is a number. The expectation value equals to 1, which is correct, equals to lambda 1. Right? So here just to show you that, oh, it is correct. I'm not proving anything. Now let's look at another example. Now I have a V which is more complicated now, which is 1 over square root 4. That is the one we had earlier. The pure state we had earlier, right? 1 over square root 4, 0 plus square root 3 over, I need square root 4 also. 1. I write in the column form, what is this? 1 over square root 4, 3 over square root 4. Is this okay? Clear? Just a given state. I hope you are very familiar with this. 1 over square root 4 part of 0, 3 over square root 4, square root 3 over 4 part of 1. Then this is the column. Yeah. Yes, thank you. Thanks for catching it. The whole thing is square root. Yeah, thank you. Any questions? So now I want to say, hey, now I'm going to do a math. This is the state of my electron. Now I'm going to measure the spin, right? Use sigma c. What is the FH value I will get? Sometimes it will collapse to 0, give me 1. Sometimes it collapse to 1 state, give me negative 1, right? Experimentally, I can only measure the eigenvalue. I actually cannot see the state, right? I cannot see that it is standing up or standing down. I get the eigenvalue in my experiment. So what is the FH value? So if we trust this equation, then it's going to be V, M, V, right? And now the V is 1 over square root 4, square root 3 over 4, and M is sigma z still 1, 0, 0, negative 1. And then V, this is 1 over square root 4, square root 3 over 4. Okay, so I continue to do the math. 1 over square root 4, square root 3 over 4. And then I will do the multiplication of the matrix on the column. And of course, again, this is inner product. 1, 0 times this one, right? So you will just pick up 1 over square root 4 because 1. Here, 0, negative 1 times this one. You will only pick up square root 3 over 4, but with, thank you, with negative inference, right? Then I continue to do the inner product. This is only just equal to 1 over square root 4 times 1 over square root 4 minus square root 3 over 4 times square root 3 over 4, which is equals to 1 over 4 minus 3 over 4. I deliberately write in this way, which is equal to 0.25 minus 0.75. And yes, equal to negative 0.5. This is the FH value. But look at this. You see that I don't get negative 0.5 out of nothing. It actually is due to 0.25 minus 0.75. Remember that at the beginning I say this one has 0.25 of chance of getting 0, which give me value equal to 1. And I have 0.75 of chance of getting state 1, which give me the eigenvalue of negative 1. So if you did not learn any quantum mechanics or linear algebra, just someone tell you about that, how do you find the expectation value? The probability of getting 0 times its eigenvalue, right? Plus the probability of getting 1 times its eigenvalue, right? And this is exactly what you get when you go through this math. This is just the 0.25 times 1 plus 0.75 times negative 1, where 1 is lambda 1, negative 1 is lambda 2. This is the probability of 1. This is, let me call it 0. Probability is 0. This is the probability of 1, right? So after all, your average value is the probability of 0 times what you measure, plus the probability of 1 times what you measure. And this gives you negative 0.5. Right? So this one will be very useful because you don't need to go through those complicated math or thinking, right? I actually have this one, want to say this is just equals to summation probability of I times the lambda value. That is the meaning of the average. Right? If you know what you are going to measure, what you are going to get, and those what you are going to get are the eigenvalue of the matrix, as we said many times. You measure something, in that experiment, it corresponds to an observable, correspond to an operator. And what you get are the eigenvalue of that operator. Right? So what you are going to get is going to be weighted sum of lambda I by the probability you will get that particular eigenvector. Yeah.
So that's an alternative way to. Can you also do
that we will go to the, yes, that we will go to the mixed state. So now I'm going to talk about pure state, right? Yeah, mixed, it is just a special case. So I'm trying to develop it step by step. Very good, yeah. So you either do a very low level, like statistic 1 probability times the value, sum them together, or use this way, the expectation value, right? That's one way. Then how about the density matrix? So let's take a look how we can do it. This is a little bit complicated. So, and that is the one of the motivation to use density matrix, right? So let's look at the mixed state expectation value. So you give me a lot of, a mixed state with all this distribution, and I really don't know the details. I only have the density matrix. Then naturally, I want to know, right, if what is the expectation value when we perform a particular measurement. So the expectation value naturally equals to this, right? I have, again, k different pure state in this density matrix. What is the FH value when I do measurement? Then I consider individual pure state first. Isn't the individual pure states has this expectation value? This is the mean outcome of each pure state. Writing is really bad. This is the mean outcome, right, of each pure state. Is this okay? Right? You have a pure state, right? It can be very complicated. One of the pure state can be this one. So this is the mean for the ith pure state. But have many different states, of course, then what do you need to do? You need to weight it with the probability of having that state, right? If I have two, one has 50%, another also 50%, then when you do the measurement, you will weight it by 0.5. If one of them is very few, let's say 1%, then its contribution only 1%, the other is 99%. So similarly, you will do this for others, right? So that is the what you will do statistically. Okay. Then we are not going to prove it. I will just give you as it is. I'm not proving, right? Because of time. It is pretty lengthy and also troublesome. Given. It's given this one is just equal to like what you say, the Ch6 of m summation I equal to 0. I give this one to you because that can guide you on how to prove it. It's happened that equal to the Ch6 of m times this matrix. What is this matrix? Density matrix of the system. Very good. So that means this is equals to the Ch6 of m times rho. Now then, another thing you need to learn about the property of Ch6 is that it is cyclic. You can rotate it. So you just imagine this is a ring, right? So now you have m at the beginning. You can make m to the end, and then this row will go to the front. It's just like a round table. Although you only have two persons now, it's a round table, right? They are still the same. Row m. Okay, you can rotate them. This is just a property of density matrix, okay? Any questions? But then what did we say about density matrix? It's Hermitian. So this is also equal to rho dagger m, right? From here to here, just because Ch6 AB equals to Ch6 BA. You need to memorize this. From here to here, it's just because rho equals to rho dagger. It's Hermitian. We talked about this before, right? Do you still remember what is this? Ch6 of the complex, the transpose, the dagger, or the adjoint, right? The adjoint of a matrix and another matrix. What do we call this? We just learned it in the last lecture. No one study, huh? Positive? No, last lecture. What is cat, bra times cat? Inner product. That's inner product of vector. This is the inner product of matrix. So here show you something very, this is very beautiful, right? The expectation value of a complicated system in a certain measurement is just equal to the inner product of the density matrix, which represent that system, and the matrix correspond to that measurement, right? Which makes sense again, right? The inner product, how much they overlap, you can think in that way. If they don't overlap at all, maybe then you don't, I don't know what you mean. Then it just all gets zero. That doesn't make sense. I cannot say that, yeah. So turn out that the expectation value of a complicated system, you cannot use this because it's not a pure vector. You just find the inner product of the matrix and the density matrix. Okay, and after all, this is also something similar. It's just the inner product of the vector with the vector transformed by that operator, right? So this is the inner product of the density matrix with that operator. And I'm not good enough to go deeper, but I hope you can think more of some correlation. Probably mathematician can give you something even better explanation why this is so, right? So let's take a look. For the system we have, I'm doing sigma z, and I want to measure this 1/4, 3/4. This is the what? This is the mixed state that we had earlier, right? So it's just the trace, because it's Hermitian, so I swap it around. Sigma z times the density matrix of the mixed state that we had, right? Maybe I write better. Let me write it better. This is just like sigma z times rho equals to this, and it equals to the trace of 1, 0, 0, -1, 1/4, 0, 0, 3/4. I will just do the multiplication. It's just equal 1/4, 0, 1/4, 0, and then 0, -3/4. What is the trace? 1/4 minus 3/4 equals to -0.5. It's also 0.5, but again, this is very easy to understand because this density matrix comes from this population. 25% 0, 75% 1. So 25% will give me 1 as the output when I do the measurement. 75% will give me -1. And this is exactly what you tell me. 25% give me 1, 75% give me -1. So the FH value is -0.5. Right? So everything makes sense. So make sense is good, but practice this, and now you know that the expectation value using density matrix is just the inner product of density matrix and the matrix correspond to that measurement. I keep emphasizing this is the matrix or operators correspond to that measurement. It does not do that measurement. It just corresponds because its eigenvalues are what you get in the experiment, in the measurement. Is this okay? Very good. Yeah. So not difficult. You just need to practice. And yeah, I also forgot actually, right? He just asked me the trace and I forgot. So here are the summary. You go back to read it. There can be typo, so I don't take responsibility. You need to double check, right? So if you copy the wrong